we can start. Yeah, you good to start? Yeah. So, hi everyone. So it's a pleasure to have Katy Snow from Queen's University in Belfast. Katy is a second year PhD student at the School of Mathematics and Physics. She's unlucky enough to work with me. She has been interested in characterizing the process of emission of entangled photons from condensed matter, solid state emitters. In particular, she has been busy with developing some techniques to go beyond a phenomenological analysis of the process itself, including the effect of an environment. So I guess that this is the topic of what she will be talking about today. And thanks, Katy, for coming over. Thank you.
Thank you. So yes, I've been modeling the dynamics of quantum dots, and specifically the dynamics under non-Markovian decoherence, which is induced by the phenomenon. So quantum dots can be used to generate entangled photon pairs. So if they're initialized in the doubly excited state, which is the bi-exciton state, labeled XX, then they have two possible decay pathways. Either they can emit two horizontally polarized photons or two vertically polarized photons, leaving the photons in the Bell state. So the aim of this work was to look at the decoherence effects present and model these, find the optimal parameters for an experimental setup. So entangled photon pairs can be used for quantum communication, either over short distances, which is what's been shown so far experimentally, or in the long term we would want to do long distance quantum communication, which would be aided by the nuclear spin back that quantum dots couple to, and that can be used as a quantum memory, allowing these to be potentially used in quantum computer nodes. So experimentally, a group in Rome has shown quantum teleportation between two different buildings, and however their teleportation didn't compare to what was previously been achieved using either spontaneous parametric down conversion sources or coherent laser pulses. And then another experiment showed entanglement swapping, but this is still below the threshold required for secure communication. So I would want to find the parameters necessary for minimal decoherence, allowing this experiment to become useful. So there are three main decoherence effects. Firstly, imperfect initialization in the bi-exciton state of the quantum dot by finite laser excitation pulses. This results in stark shifting of the intermediate exciton states, and this introduces switch path information between the two different decay paths, which can be partially solved by embedding the quantum dot inside a monophotonic cavity, which would be resonant. The two photon transition would be resonant with the bi-exciton state, and therefore decay wouldn't have to happen via the intermediate exciton states. And then we also have fine structure splitting, which is what is responsible for that rich path information. And then finally, phonons in the substrate cause Markovian decoherence, so they have some kind of memory effect which occurs on nanosecond timescales. So there are lots of different possible numerical methods available for modeling the non-Markovian decoherence. I have a list of them here, but the ones that I eventually converged on were the Polaron master equation technique, which is an method that works well when decoherence due to the non-Markovian environment happens on a much faster time scale than the system dynamics. And then, secondly, I used the numerically exact tempo method, which stands for time evolving matrix product operators, and a formulation of that in terms of process tensors. So the process tensor method is a discretized path integral method, and then that allows the action of the environment to be expressed as a tensor network, which can subsequently be contracted and compressed to create a process tensor, which can be used to evolve your system density matrix. So this equation describes the propagation of the initial state rho naught of the system to the state of the system at time n or n dt, where dt would be the time step. And the system is propagated firstly by the free system dynamics, which is specified by this matrix U, and then process tensor, which encodes the effect of the environment. And this equation is represented graphically over the end there. So the initial state rho is propagated by the free system operators, which are the pink squares, and then the environmental process tensor, which is the part in blue. And for this work, I have had to extend this method to the case when our system can be split into a part which interacts with the environment and a part which only interacts with the other subsystem. And this allows for propagation of a system density matrix when the Hilbert space of the system is large, which wouldn't otherwise be the case because calculating the process tensor for large Hilbert spaces is very difficult. And then my free-system dynamics, I'm looking at a quantum dot and coupled to a bimodal cavity, which enhances the two-photon emission channel so that the quantum dot doesn't have to decay via those intermediate exciton states which cause decoherence. And then I'm also including a laser excitation pulse, which is resonant with the two-photon excitation transition, and looking at the concurrence, a measure of the entanglement of the emitted photon pairs. So my Hamiltonian contains a quantum dot, the interaction between the quantum dot and the cavity, and then the driving term. And I'm also including limb-like decay of the cavity. So numerically, I have modeled the system, firstly in the case where there is no excitation pulse, so the system is perfectly initialized in the bi-exciton state XX. And then secondly, also including the laser excitation pulse. So when we just initialize in the bi-exciton state, what we see is that when there are no phonons present, which is the grey lines, the concurrence or the entanglement of the photon pairs is higher than it is when you include the effects of the phonons. And I also found that the two different numerical methods agreed quite well. So the Polaron master equation, which is just approximate, gives a good approximation to the numerically exact result. And then I also modeled the system in a reduced Hilbert space, and this gives the same result as in the entire Hilbert space for this particular situation of where there is no laser driving. And then finally, I looked at what happens when we initialize in the ground state of the quantum dot and then apply a Gaussian excitation pulse. So we start in the ground state. The ground state becomes depopulated during the pulse, and the bi-exciton state becomes excited, and then the bi-exciton state decays back down again towards the ground. And I found that the concurrence is much lower during the period when the excitation pulse is present, but then relaxes or returns to its previous level. So, and also that the phonons always cause a reduced concurrence compared to when there are no phonons present. So, using the polar master equation method, since this is much easier to do numerically, is I've looked at the trends of the entanglement versus the pulse width and temperature of the phonon back, and found that the entanglement decreases with the pulse width and also decreases with increasing temperature, and this is a compounding effect. So that would agree with previous studies which have looked at these effects in the absence of a cavity. And mine goes beyond their studies because including the cavity is difficult for these non-Markovian dynamic simulations because it's a large Hilbert space. Okay, so finally in the future I want to look at different figures of merit of these entangled photons besides their entanglement, so also the efficiency and indistinguishability of photons, and find the optimal parameter regime for example, a cavity coupling and cavity decay rates. And then another idea would be to look at this different quantum dot configuration, which is used for generating cluster states, and look at the effect of phonon decoherence in that case. So that's it. Thank you.
Thank you so much, Katy. So, any question? You can't ask questions.
Can you go back one slide? Can you say something more about this? How does the void geometry work in the context of cluster space generation? Yeah.
I don't know a lot about this, but yes, you would have to look at this paper at the bottom there.
It's like, what do you mean geometry there? Like, is it like configuration of the quantum dots?
So
or
they apply a magnetic field, and that results in this different energy level structure compared to when there's no magnetic field.
Okay.
So I think it's jargon for the model that describes the levels of the dot that are involved in the emission process.
Because it's like the geometry of the level, not geometry of the cluster.
It's the geometry of the level configurations that are coupled to the lambda e, right? So no, it's just so you don't have to think about the geometrical average. Okay.
So like lambda versus
Yeah, it might be I would say a special configuration of in energy levels.
One question I have, I think the focus on quantum dots will be to use them to make quantum networks, right? All the quantum state. No? But is there any way you can implement this polarization entanglement to make operations like joint measurements or things like this? Experimentally or theoretically? because I have no idea.
Joint measurements within
Joint measurements like do state measurement over two different photons.
What you do in that case is that you make the photons interfere at a beam splitter and then you perform local measurements. Okay, so that would implement your bell measurement.
Okay, but now they to interfere the polarization of the photon.
So you split them, and then, so the idea is to use different sources probably generating different bits. For instance, in this case, in the case of photonic cluster states, so this is one way of measurement-based quantum computation. You make different sources interfere. You build up a large cluster state or a large enough cluster state. Then you start performing local measurements. So individual mode measurement to process information.
Okay, so the quantum dots are used as just a creator source of entangled photons. Okay, and you can, in theory, also create multiple purification, I guess. Yes, okay.
Instead of using, I don't know, nonlinear crystals to generate light, the entangled light, you use these guys that you can integrate better into fibers. They have higher repetition rates. They are certainly more scalable.
And do you think there are any implications how polarization entanglement degrades states, like because you start in a pure state, do they degrade, they become very mixed if they go through fiber optics? No?
You want to?
Yeah.
Okay.
I don't know whether the polarization degree of freedom is any worse than maybe the degree of freedom for engaging users.
Yeah. Typically, you have mechanisms that spoil the quality of your states. If you work in fiber, you have dephasing after a certain length.
Sure. Sure, no, but the thing is that this encoding polarization is, I don't know, makes me think they are maybe better for this.
It depends on what you want to. Depends on what you want to. Sujin can talk of say number photon, say photon numbers. Photon number encoding as a better way of, as a way of making, for instance, certain protocols for QKD more robust.
Sure.
Than those based on polarization.
Sure.
Polarization.
Okay, thank you.
Any other questions? If not, we thank Katy again.